Hey guys, we're going to start our next video on ecosystems. I'm sorry if you hear some weird background noises. I'm doing this one while the sun is still up, and so my sons are still up, and so they're kind of noisy. But I wanted to get this one out to you so that you had time to watch it before class. So essentially, the other day we talked about trophic levels. In our last video, we talked about various levels of basically energy flow. And we didn't really talk about it in terms of energy flow. We talked about it in terms of feeding. Trophic levels are essentially what feeding is. And so we talked about things like producers, okay, things down at the bottom level that are going to convert usually sunlight into food. And then obviously we've got consumers, okay, and so everything from there on up, everything except the very base layer there, the producers are the consumers. And so then we've got different levels of consumers. We got primary, then we got secondary, and then tertiary. Now, normally in most times, even though we can go above tertiary, we don't often label it above tertiary. Usually we kind of stop there, but there are things above tertiary. There's quaternary and stuff like that as far as trophic levels go as well. Now, how does all of this deal with energy? Well, first off, we talked about that food chain, and so we had that really simple. Let me jump back one slide real quick. We had this really simple food chain where it just sort of went up in a nice vertical, even line. But in reality, that's not the way that feeding and trophic levels actually work. This is actually a really good example of a real life, what we call a food web, as opposed to a food chain. And most of what we're going to deal with in APES is going to be food webs, because food chains are kind of a nice, simple, elementary thing, but in reality, much more complicated situation. Now, if you notice, things are pretty similar. Okay, so down here at the very bottom level, we've still got producers. Okay, we've got primary consumers, okay, which are herbivores, and really, I mean, you can sort of see the way this is labeled a little bit. Really, technically speaking, these herbivores here probably would be the primary consumer level as far as we're concerned. And then what they're actually talking about here in this diagram is primary carnivores, really. But still, same basic principle. So we've got producers, primary consumers, secondary, tertiary, okay, apex predators, okay, the top of the food chain, top of the food web here. And the difference between a food chain and a food web, you'll see, is that obviously it's not going in a straight line, that there's a lot of back and forth. There's a lot of things that are eating different things, and so the phytoplankton are getting eaten by, by stuff like shrimp, and they're getting eaten by small fish and by mollusks and oysters and stuff like that. And then those things are getting eaten by different things. All kinds of different fish, or all kinds. These small fish here are being eaten by all kinds of different animals. And then obviously, if they're being eaten by bigger fish, then those bigger fish are eaten by bigger birds, and so on and so forth. So just remember the idea that it's much more complicated than that sort of simple food chain idea that we might have had from elementary school. So a little bit of terminology here. We're going to take all of the weight, all of the mass of all of the organic matter at one particular trophic level, and we're going to call that the biomass. Now, we could do it for a whole ecosystem. In fact, we do that a lot of times for specific studies. We'd say that the biomass of this area of this swampland is, this is the biomass of it. But the way we're going to look at it is we're going to be talking about trophic level or trophic level. And so we've got the biomass here is where we're going to get the energy from, okay? Remember that for us, energy in this case is chemical energy, okay? And it's stored in food. It's stored as glucose and as proteins and as other forms of food. But, sort of glucose being that primary mechanism that we get our ATP and all that stuff from in cellular respiration. So the chemical energy is stored, and then it's going to get transferred from one level to another. Okay, now, a couple of things that we need to review real quick as we talk about that energy transfer. So the first thing is the first law of thermodynamics, okay? So if you recall, what does the first law of thermodynamics say? Okay, pause real quick and just see if you can remember what it says. Okay, so that's right. First law of thermodynamics, conservation of energy. Okay, can't create or destroy energy. We can only transform it from one type to another, right? Okay, so we don't create or destroy energy. Energy is basically transformed. And again, recall that there's some sort of nuclear type stuff that makes some of this seem sort of weird. But in general practice, conservation of energy, can't create or destroy energy. Now, if you recall, what does the second law of thermodynamics say? And if we just had to like sum that up in one word, we would say that was entropy. But really what that means is that we're going from high quality energy, okay, to low quality energy. In other words, we're going from something like chemical energy into heat energy, or we're going from electrical energy, and some of that is lost as heat energy. And so you got these two laws of thermodynamics. And remember, thermodynamics basically means energy, okay? And so we got these two laws here. It says that we can't create or destroy energy, but the second law of thermodynamics says that the natural tendency is to go from high quality energy to low quality energy. So that's going to lead us into this idea. That's going to sort of be our fundamental principle of energy as we're talking about how it flows in ecosystems and our trophic levels. We don't create or destroy energy, but the quality is pretty much always lowered as we convert that energy from one form to another. So the easiest way to see this is usually with what's termed as an ecological pyramid or a trophic level pyramid. So we're going to sort of walk through this. I'm going to start here at the bottom and we'll build up and we'll see how this shows that sort of shows the energy changing its situation. Okay, so we start at the bottom. Got producers. Typically producers, now we would have plants there maybe if we're talking about terrestrial or land-based organisms, but I'm sort of doing a marine example here. So phytoplankton, or not a marine, a freshwater example. Phytoplankton, little tiny microscopic organisms, they're called phytoplankton to distinguish them from zooplankton. Zooplankton are animals that eat the phytoplankton, so the phytoplankton produce their energy from photosynthesis, so they're the producers, okay? Up a level from that is the primary consumers, which are the zooplankton, okay? The herbivores, they're herbivores, they're going to eat the phytoplankton, okay? So a couple of things I want you to note real quick about this diagram, other than there's a bunch of stuff here that's a little bit confusing. So first off, phytoplankton die if they're not consumed. A lot of that energy is then going to get lost to heat. Decomposers are always part of the equation here. We're going to talk about the pyramid sort of up here in a triangle type shape, but off to the side is almost always some sort of decomposing organisms taking up some of this stuff. And so what you notice immediately is we're going to assume that I've got like 10,000 kilocalories, okay? And I forgot to write that on the slide, so we'll just write it in right now. Okay, we're talking about kilocalories. That's sort of our fundamental unit of energy. That's how much that our given sample here of phytoplankton has. As that energy as those phytoplankton get consumed by the zooplankton, that energy goes down to 1,000. Essentially what that means is that if you'll notice that that's only 10% of the original energy. So what that means is that 90% of it, okay, is lost basically to heat. It's lost to entropy. It's lost to that second law of thermodynamics. It says that it was a high quality form of energy, and some of it is still high quality, this 1,000, but that most of it went off into heat in the process of consuming, and some of it went to the decomposers. And of course the decomposers are using energy too, but they're losing a lot of their energy to heat as well. Okay, so 90%. Go to the next level. Let's say that some fish, some perch, are eating the zooplankton. Okay, so they're the secondary consumers. They're carnivores. They're eating the zooplankton. And so that then means that, again, we lose another 90%. 100 is only 10% of 1,000, and so we've lost another 90% to heat. And what we'll see is that essentially that's the case every time we advance up a trophic level, is that we're going to lose 90% with each stage that we go through. And so what does that leave us with? Well, that is going to leave us with, okay, pardon my terrible drawing skills, but essentially a triangle or a pyramid if we were in 3 dimensions. That shows us that we lose a lot of energy each time we transfer the energy from one source to another. Now this has some pretty important implications. It has some implications like, say, to the idea of, hey, ecologically speaking, and I'm not talking about morally or ethically or anything like that, but ecologically speaking, probably be more beneficial if we were vegetarians as opposed to omnivores that we typically are. Now, I mean, I'm a meat eater, or I'm an omnivore. I had a hamburger for dinner, so I'm not saying morally or ethically that it's necessarily the right choice, but ecologically speaking, definitely a lot more efficient, at least, to be at this level, because if we're up here, and let's be honest, quite often we're actually a level or two above this even, and so it takes a lot of plant biomass and energy to be able to support people higher up at the the top of that ecological pyramid. That's a pretty important thing. I mean, just think, if we were down here at this level, yes, we're losing 90%, but we're not losing 99 and then 99.9 and 99.99% each time as we go up the chain. We're losing a certain amount, but we're being a lot more efficient the lower down the chain we are. Okay? So again, not making any ethical or moral judgments there. I mean, that's sort of beyond the bounds of our of this discussion, at least, although we're going to talk about it. But efficiency-wise, definitely more efficient to consume as far down the food chain or the food web as possible. So a couple of things you want to make sure you get out of that. Make sure that you get that 90% number. Okay, that number, super important. I'll write it up here again just to make sure. And of course, that's a rough estimate. That is not always true. But in general, the rule of thumb is that you lose 90% every time you go up a trophic level. Okay, now, a couple of other things that are going to influence this. Well, to be perfectly honest, some ecosystems produce plant matter a lot faster than others do. Okay, if we're comparing, say, desert to rainforest, I mean, obviously the rainforest is going to produce a lot more biomass, a lot more plant at the same rate that the desert produces it. And that rate of production is really important to us also. It's not just a matter of how much mass is there, but how quickly does that mass grow? Because if what we're talking about is in trophic levels is feeding, and we're consuming some of that biomass, what really matters for us ecologically and efficiency-wise is how quickly can that be replaced. And obviously in the desert, it can't be replaced terribly quickly. In some place like a rainforest, yeah, that biomass can get replaced pretty quickly. Now, of course, you have to stop and consider, too, how much of this biomass in the rainforest is edible as compared to how much of this is edible. And again, that goes to, hey, maybe humans can't eat all this biomass, but maybe some other animal could, and then we could consume those animals. Okay, so all of that sort of has to go into our thinking about these processes. And I grabbed this image from Algebra Lab. It's actually pretty cool because I grabbed this image from the site that does some math testing and graph reading, but they had this pretty good image here. And there's an even better one in your textbook that sort of shows you about the productivity levels of various ecosystems or various biomes. And what you'll notice is right up here at the top, the very tip-top things, okay, estuaries, okay, and we'll talk about biomes a little bit later, but that's, you've got water coming out towards a bay or something like that, and you've got a lot of area around there that's extremely rich in nutrients because as stuff flows out of the rivers there, it's carrying a lot of nutrients with it. Swamps and marshes actually, depending on the graph, and I think the graph in your book actually has that even more productive than a tropical rainforest, which is sort of, at least for me, kind of like the baseline when I think of like high productivity levels. That's what I'm thinking of. And then forests, of course, are pretty productive. Believe it or not, taigas are pretty far up there. Savannas, and then you see agricultural land kind of here in the middle. Okay, and now remember, we're not talking about necessarily edible crops for humans. We're talking about its general productivity for biomass that's producing. Okay, and then obviously as we get down to the desert and the extreme desert and the tundra and out in the open ocean and stuff, not a lot of productivity per area of space. Look at the units here, kilocal per meter squared per year. Now that leads us into some definitions that we're going to need to know. You're going to see pop up all the time in FRQs and certainly at the end of the year. So our first one is gross primary productivity, or GPP. And that is the rate at which an ecosystem's producers convert the solar energy to chemical energy. Now, what I want to underline here for you is the rate. Okay? It's not how much biomass is there, because if it was just how much biomass is there, there's a lot more in the open ocean overall than there is just about anywhere else because there's more ocean. Okay? But it doesn't produce at a very high rate. And so that's the primary productivity that we're talking about. Okay? In sort of social studies terms or economics terms, you can kind of compare that to GDP. So GPP is our sort of ecological GDP. Okay? It's how much overall productivity there is. Okay? Again, like that last slide, the unit for this usually is going to be kilocalories per meter squared per year. Doesn't have to be. It can certainly be kilocalories per hectare per year. Okay, term that we know pretty well, right? Remember what a hectare is? We did all of our activity on that, so hopefully you remember that. But usually when you see this in a paper and a graph, it's going to be meter squared. Kilocalories per meter squared per year is going to be that GPP. Now, of course, the fact of the matter is, while a certain ecosystem can produce at a certain rate, that's not all that matters, because what also matters is how much of that energy that it produces does it consume itself. Okay? So I like to think about this. I mean, if you think about it in terms of like paycheck, if you guys have a job. So like I remember I worked at a grocery store called Publix when I was in high school. And so, you get paid a certain amount, which was really low for me because I'm old and it was a long time ago. But you had a gross paycheck that was like what your actual what your actual hourly wage was. So like, let's say that you were getting paid $6 an hour and you work 20 hours and you're like, sweet, 120 bucks. Well, of course, that's not what you actually get in your paycheck. What you get in your paycheck is your net pay, which is after they take out Social Security and income taxes and Medicare insurance, and if you had insurance premiums and all that stuff. And so $120 paycheck for a week or for 20 hours all of a sudden becomes $70, and that's your net productivity or your net pay. And so that corresponds pretty much exactly to the idea of net primary productivity, or NPP. I didn't write that here, but that would be NPP. I should probably write the pen. I've been writing with the mouse. Okay, sadly not much better. So your net primary productivity is your GPP minus all of the energy that the producers themselves are using. Okay, so what does that really mean? Well, essentially we kind of break down our energy flow like this. So the sun obviously is where we're going to get most of this energy. And again, I know, yes, there's chemosynthesis and stuff like that. So it's not all from the sun, but the vast bulk of what we're worried about is. About 99% of the energy that the Earth receives from the sun doesn't really get absorbed by plants or producers at all. It's going to get reflected. It's going to go through the plants. It's not going to get it absorbed at all. So that leaves essentially, that is going to leave us then 1%. So that is going to leave us then for what we're actually worried about. We're talking about 1% of the total energy from the sun essentially goes into the plants. That's the GPP. Well, the way that breaks down then is that a certain amount of that, and I believe, so what that leaves us with then is 1%. So 99% of it doesn't go to the plants at all. 1% of the solar energy gets absorbed by the plants. And then of that 1%, a certain amount of it is lost just to respiration. And that amount is about 60% of that 1%. Okay, and so that means that our net primary productivity is 40%. And remember, if that's 40% of 1%, then that means that essentially 0.4%, okay, of the total energy from the sun is the net productivity. And that's a pretty relatively small amount. Now, the good news is the sun sends to Earth a ridiculous amount of energy in the first place. And so it's still a lot of energy. Now, what's important here is that this NPP, this amount of energy that the plants actually have available for other organisms to use, that sets a limit there on how many consumers can survive on the Earth. Because that's all the energy that's available. And remember, each step you're removed at the trophic level, the available energy goes down, because that second law of thermodynamics basically trims that by 90% every time that it gets dissipated away into heat energy. Energy's still there, but not really in a usable form in that case. Okay, so hopefully this gives you a pretty good clue about how the energy flows through ecosystems. What we're going to do in the next video is we're going to talk about the flow of matter through the ecosystems. Also important, I'm not saying it's more important, equally important I would say, that we know how both of these things work through ecosystems.